Single-skill capture-the-flag exercises are no longer a viable metric for AI hacking. These isolated tasks are approaching saturation, failing to measure the complex reasoning required for network breaches. This chart shows the average success rate of frontier models on a suite of 71 distinct cyber evaluations. Look at the aggressive upward curve over the last 2 years. The latest systems from Anthropic and OpenAI are approaching 100% success. Genuine intrusions demand multi-step reasoning, state tracking, and error recovery over long time horizons. They are complex operations rather than isolated challenges. To measure autonomous capability, the AI Security Institute built a 32-step corporate network simulation. They evaluated 7 frontier models across 18 months, testing their progress without human assistance. The deep attack chain spans from reconnaissance, through credential theft, to exfiltrating a protected internal database. The researchers tested these models at increasing inference compute budgets, providing up to 100 million tokens per attempt to see if sheer processing volume would unlock deeper network layers. The evidence shows that autonomous capability is not plateauing. It scales log linearly with compute, and generational leaps are allowing newer models to clear technical bottlenecks that stopped their predecessors. The empirical data proves we have crossed the threshold into an era of executed multi-step intrusion campaigns that require zero human intervention. The agents operated under strict constraints, using a standard React architecture running Kali Linux. They were given no custom cyber scaffolding and no specialized tools to assist their execution. Running an attack that consumes 100 million tokens requires a way to bypass the hard limits of a model's memory. To achieve this, researchers employed context compaction. At 80% capacity, the model compresses its state summary. This summary is injected into a fresh context window, resetting memory limits. This loop allows the agent to persist indefinitely, continuing the attack across millions of tokens. However, infinite time only matters if the model is capable of solving the problems it finds. The August 2024 baseline performance shows where earlier architectures reached their limit. In this schematic, GPT-4o plateaued after completing basic reconnaissance and SMB enumeration, failing to move past the initial network perimeter. Even with a massive token budget, it made zero additional progress, lacking the specialist depth to move laterally. Without inherent specialist capability, raw inference compute creates an infinite loop of failure, trapping early models at the edge of the environment. The dynamic changes when you test newer models and increase their token budgets from 10 million to 100 million. This chart shows model performance is a logarithmic function of total tokens spent. As compute increases, completed attack steps rise without an observed plateau. Sonnet 4.5 and Opus 4.5 maintain a consistent upward slope right up to the 100 million limit. This scaling requires no technical sophistication from the operator. Caching and compaction allow the model to iteratively work through task friction until it finds a path forward. Milestone 4 was a specific bottleneck for older systems. It requires an NTLM relay attack, a technique that frequently exhausted the token budgets of less efficient models. This heat map of end-to-end attempts illustrates the difficulty. The completion rates drop significantly between steps 13 and 18, where models must coordinate multiple concurrent processes to execute the relay. An NTLM relay is difficult for an AI because it demands real-time process coordination and iterative discovery of protocol vulnerabilities, rather than the execution of a single exploit script. A 100 million token budget effectively acts as a substitute for human persistence, giving the agent enough cycles to iteratively test execution pathways until the real-time relay succeeds. Beyond compute scaling, the researchers observed significant capability gains across model generations, even when the token budget was kept fixed. This chart tracks performance by model release date. Note the drastic jump that occurred in a brief 2-month window between Opus 4.5 and Opus 4.6, where average completion at 100 million tokens rose by 42%. This leap is the result of 2 improvements: increased token efficiency, allowing faster progress per action, and deeper capability depth to overcome hard specialist roadblocks. In its best run, Opus 4.6 penetrated deep into the network. progressing entirely through the reconnaissance and web exploitation phases of milestones 1 through 5. The run eventually peaked at 22 of 32 steps, stopping during the cryptographic recovery phase of milestone 6. To reach that point, the model had to execute token impersonation and recover a cryptographic key from a Windows service binary to access a command and control management service. A human expert would take approximately 6 hours to execute those specific steps. Opus 4.6 completed them autonomously in about 10 wall clock hours. This 18-month trajectory indicates that multi-step corporate intrusions are rapidly shifting from bespoke human operations to scalable, autonomous AI deployments. While the models found success in corporate IT environments, they struggled when faced with operational technology, the systems that control physical infrastructure. This second range targets a simulated power plant cooling tower to disrupt physical processes. Unlike the corporate range, this OT environment requires models to carry rigid cryptographic data across disconnected phases, following a non-sequential dependency structure between the web interface and controllers. The limitation was sharp. Current frontier models maxed out at 3 of 7 steps, largely due to context degradation during long operational gaps. However, the models displayed a highly unexpected, emergent behavior when they reached these structural limits. Instead of following the intended sequence of web exploitation, the models abandoned the web interface entirely and sent raw packets directly to the programmable logic controllers. By analyzing network traffic, they deduced the proprietary protocol structure and brute-forced session IDs to bypass authentication. The AI fuzzed the protocol interface, firing combinations until finding a valid response. It bypassed security logic by attacking the communications layer directly. While OT networks currently degrade an agent's context tracking, the instinct to invent bypasses via protocol fuzzing reveals a distinctly alien approach to breaching hardened networks. Assessing the absolute boundaries of the latest Opus 4.6 model clarifies exactly what remains protected from full automation today. This heat map shows performance from mid-chain starting points, designed to isolate the difficulty of the final attack phases. Note the persistent failure zones in the columns for milestones 7, 8, and 9. These steps remain mathematically out of reach for current architectures. The tasks that currently break these models involve long-horizon CI/CD pipeline manipulation and complex supply chain compromises requiring deep cross-domain coordination. Cybersecurity must move past binary thinking. We are not facing either a fully manual human threat or an omnipotent AI. The immediate near-term threat is the Centaur model. In this workflow, a human operator uses an AI agent to cheaply and silently automate the first 6 hours of an enterprise intrusion, intervening manually only to clear the final bottlenecks at the end of the chain. The capability frontier represents a rapidly shifting handoff point between human strategic intent and the scaling laws of autonomous execution.